Okay, so first I will start with an example and then we'll go into the lecture. I am considering the following language. Can everybody see my screen?
Okay, I mean, if you are not comfortable, I can take it.
I think it'll be fine. Let me just check because I don't know how long the lockdown will go on. So I need to try this out.
Yes, ma'am, we can see the screen.
But
Okay.
this is actually I mean, not a full screen type of thing, right? If you can manage, it's fine. I can also take, no problem.
Yes, ma'am. Now it's better.
No, I think the earlier thing was better. I think you are not audible. I cannot hear you.
Hello, can you hear me now?
Yeah, now it's fine.
So can you see the screen now?
Yes, ma'am.
Okay,
Yes, ma'am.
this is the language, and I want I want I want to see whether this is I want to check whether this is a regular set or not. How will you go about it?
We can try to make a DFA.
Okay. So what will the states of your DFA be?
Can you show the question again?
So the question is, you want to accept the language which contains all the strings from 0 1 star, where the fifth last element is 1. Fifth last element is 1.
Okay, ma'am.
Can we create a machine which in which the states are the fifth last element itself? So that has let's say four nodes which denote the starting, which are for the starting itself, and then from the fifth node we can just use the information from the first character somehow.
So in your DFA, you have you have 5 nodes, 5 states. Hello?
Ma'am, I'm not exactly sure.
Okay. So think about it for a little bit more. What can the states be? You have to remember the yes.
And we can do something like this. It will be a little bit big. I mean, first we have a start state, and from here we will have two states, one for 0 and for 1. Then we can continue dividing each of them into two of them up to 5 levels, and then at the last level we will check if it has ended or not. If not, then if 0 or 1, we will return to a corresponding state in the before one.
Okay, so you have 0 and 1. Then in the next level, what are you doing? Again, you're putting
splitting
0 and 1.
Yeah, and it will go on for 5 levels.
Okay, for 5 levels, and then
in the last level, in the last level, suppose in the last level, suppose if we get if there are more symbols, then we will have to return to to a level. If now we have to know for now, since we have already followed a path through this tree, we know that which symbol was which. So if there is another symbol after it, so we have to return to the state in where there was a 1. From
no, so suppose you are going down the path, let's say 0 1 0 0 1, and then you get a 0. So where will you go?
Ma'am, we will go to the path where 10110 went. If we add 10110,
so 10110 went free. And
okay,
then
so basically your idea is you're remembering the last 5.
Yes, ma'am.
You're remembering the last 5 symbols.
Yes, via the tree.
Via the tree, or if I can just rearrange what you're saying. So every state for you is a 5-length string. I can think of it as a 5-length string.
Yes, ma'am.
Okay, so now suppose for every state, let me just call it as 0. Let me just call it as 0 to the 5, and then maybe 0 to the 4 1, and so on. These are my states. So now in the previous example, if I was at, let's say, 0 1 0 0 1, and then I read a symbol 0, then now I can go to the state 1 0 0 1 0. Whatever you're saying is very similar. It is. I'm just rearranging what you're saying, just to visualize it clearer.
Can you explain this? Can you explain this again?
So all I'm saying is, let me erase this and put a different color. Okay, so the green represents the nodes. So what I'm saying is I will have 2 to the 5. So what are the possible the idea is I have to remember the last 5 symbols. So now I know that I have 2 to the, if I'm taking strings from 0 1 star, I have 2 to the 5 strings of length 5. So I create 2 to the 5 states, And now each state I am associating with one particular 5-length string. So for example, this state I'm associating with the string which is 5 zeros. This state I'm associating with the string which has 4 zeros first and then a 1. Okay, and so on. I will create 2 to the 5, which is how much? 36.
32.
32, yeah. So I will create 32 states, and each state corresponds to a 5-length string. Now, if I want to remember the last 5 symbols, so suppose the last 5 symbols was 0, 1, 0, 0, 1. So if I'm doing my transitions correctly, I will be in my state 0, 1, 0, 0, 1. Now if I read an extra symbol 0, so my input symbol is 0, then I should transition from the state corresponding to 0, 1, 0, 0, 1 to the state corresponding to 1, 0, 0, 1, 0. Right? Whoever asked the question, is it clear now?
Yes, ma'am.
Okay. So so you have
Ma'am,
two
so we
ways.
can do that. Like we number the states from 0 to 31, and 0, 0, 0, 0, 0 will go to 0, like the 5-digit binary to
Right.
decimal representation, and we go 2x plus 0 or 2x plus 1, depending on what we get.
Right. Yeah.
The next step.
Yeah, so but I haven't specified everything. So here, for example, the tree that you gave, you specified the start state and you, of course, you will also specify the final states in the 5th level, right? So in this rearrangement, you both are in this rearrangement, try to figure out what the start state will be and what the final states are. And so briefly you can understand what is happening. You have to remember the states will correspond to the last 5 symbols that you have seen in the string, and you make the transition according to the current last 5 symbols. Now you formalize the DFA. Okay, now my question, okay, so currently we are seeing DFAs where the states are around. So if the question is that I want to check whether the 5th last symbol is 1, then the states are coming to around 2 to the 5, approximately 2 to the 5. So once you formalize the DFA, my next question is, this is, you can think offline and then we come back on Thursday and try it out. Can you reduce the number of states? Can you do with 2 to the 5 minus 1 or less? Okay, so this, please try this, please formalize this exercise and try the last question. We will revisit it on Thursday. Now I come to the lecture. Please let me know if you can't hear. At some point, if you can't hear me, then let me know. Can you see the screen properly?
Yes, ma'am.
Can you see the writing?
Yes, ma'am.
Okay.
Ma'am, are you
Okay.
writing?
No, I'm not writing. Just the text. Can you see it properly or?
Yes, ma'am. Text is visible.
Okay. So today we will start with a slightly more generalized version of the mathematical modeling we've been seeing, which is deterministic finite automata. In deterministic finite automata, we wanted to keep it as simple as possible. And therefore, one of the assumptions that we made was that the transition function, the transitions will be captured by a function. So whenever I'm saying it is captured by a function, it means that I know exactly what the next transition state is going to be. So wherever I am, I know exactly what the next thing is going to be, which is what led to um, the fact that if you're at any state and you want to read a string, you want to see where a string ends when it starts from that particular state, there is a unique path with the label of the string in the transition diagram of a DFA, because we knew exactly what the next step was going to be. But that's not always the case. Even if you write a program, and suppose in a subroutine you have a case analysis, then you know that there are from the same state, from the same current um, screen snapshot of the computation system, there it is possible that there are many there are several next there are several next states depending on maybe some external conditions. So if you have a case analysis in a program, then maybe there are there are a finite set of properties for which you can solve the problem in different ways. So if you can identify these properties, then you will be proceeding in a different way. So it a natural generalization would be that instead of having an exact transition from a particular state when I read a particular symbol, it is possible that for when I read this particular symbol and I'm at a particular state, I may have an option for which state I move next. The options that are available could be dependent on what I have read so far, or it could be dependent on external factors of the machine and so on. So this happens naturally, but again we are not going to go we will not generalize so far. We will look at a slightly more general version of DFAs. In terms of definition, you will discover other things later. So in terms of definition, it appears to be slightly more general than deterministic finite automata in the following sense. So when I talk about non-determinism, I want to say that there are more than one state transitions available at the current time step, and the machine can choose between which one it wants to transition to. So then this means that I no longer require the transitions to be captured by a function. It can be a map. So depending on where I am and what I'm reading, there can be more than one stage to which I can transition to. Now, if I'm allowing more than one possibilities, another generalization could be that instead of requiring exactly one start state from which the system starts off whenever I get an input string, I could guess where the system is starting off from the state space. From this set of states Q, I could decide the machine could have the option of deciding where it wants to start off. Or I mean, instead of having one particular start state, the machine could decide that okay, this is a subset of states from which I can start off, and I will be able to choose which one I start off from. So a single start state is no longer required. These are the two basic generalizations that we are considering from the DFAs that we have seen before. So then what does this generalization capture? So the first thing that we can notice is that it is no longer, since we are not starting from a particular start state and we no longer know exactly what the next transition state is going to be, if you consider the transition diagram, if you consider the if you consider the transition diagram, then it is and you specify a particular string, then it is no longer a unique path starting from a start state, a unique directed path starting from a start state and ending at some end state. Now it could be a subgraph of the transition diagram. So you consider every path starting from a particular start state. There could be more than one start state. You consider every path that is labeled by X starting from a start state. This will give you a subgraph of the transition diagram. And the idea is that the automaton is guessing whether or the automaton is verifying whether a path exists from the start state to a final state. So earlier it was that there is one path starting from the start state, from the unique start state. If the end state is a final state, then I say that X has been accepted. Now I have multiple paths starting from could start from different start states. If at least one of the paths ends in a final state, then I say that X is being accepted by the automaton. And if no such path ends in a final state, then X is not being then X is being rejected by this automaton. Since we are no longer requiring, since we are no longer requiring a unique path to exist, it is possible that some of the paths you take off in some of the paths. You may allow some of the paths to terminate as well. Just like you, so if you consider a basic program, you allow these things. So in this generalization, we can also allow that some of the paths which we start off from a start state, you may allow them to terminate in between without reading X completely. Okay, so then these are the things that we have to keep in mind in the current model that we are trying to create. The first thing is you are allowed to make more than one transitions on reading, or you are allowed to choose from more than one options on reading the same symbol coming and being at the same state. So if you're at state Q and you're reading a symbol A, you're allowed to choose from more than one transitions. So in the transition diagram, you can think of putting more than one arrows from the state Q to the next states, depending on what are the options available from for transition from Q on reading this alphabet A. There could be multiple there could be multiple next states depending on the transitions available for Q and A, and therefore you can think in the transition diagram you have multiple arrows coming out of Q and labeled with A. Earlier you had exactly one exactly one arrow coming out of Q and labeled by A, because you needed to represent a function as you needed to represent the transition function. But now I don't require a function anymore. I just require a map. So it is allowed to put in more than one arrows, outgoing arcs, which have the same symbol labeling it. The second thing is you are allowed to choose more than one states in your as your start state. So you can now have a set of states to be your start states. And the third thing is you are allowing termination. So it is possible that you don't have it is possible that for a particular state, if you read a particular symbol, you may decide to terminate, meaning that there is no outgoing edge from the state that is labeled with A. You don't have any transition. So if you look at the map, you don't the range space is empty for that particular let's say Q and A. Since you are only allowing a map, you're going it is possible that there are no transitions defined from the state Q when you're reading an alphabet A. So if you think of it in terms of the transition diagram, so these three notes basically tell you that earlier, because I was trying to capture a transition function from every state, it must have had an outgoing directed edge labeled by, okay, so for every state and every symbol, the state must have had an outgoing edge labeled by this particular symbol. So for every state and every symbol, there was exactly one outgoing edge labeled by that symbol. Now, for every state, you can have more than one outgoing edges labeled by a particular symbol. it is possible that you have no outgoing edges labeled by that symbol. And you can have more than one start states to start off from. So now, if you allow these kind of relaxations, let us, I have not specified it mathematically yet, but just from modifying the transition diagrams, if you look at the example we considered earlier, the set of strings where the fifth last symbol or the fifth symbol from the right is 1, then if you look at the following transition diagram, this machine will be accepting the set A. Can somebody tell me why? So I'll just describe the machine. You have one start state marked by the arrow, and then you have 5 more states with the fifth, with the last state being the final state marked by an extra circle. And notice that from state 1 to state 2, so from state 1 you have 2 edges marked labeled by 1. Then in the last state, the 6th state, you have no edges going out of it. So if you read anything after that, you're basically terminating at that particular state. So now can you argue why this is going to accept A?
Ma'am?
Yes.
Ma'am, I have a doubt. So when it terminates, that means it is not successful, right?
When it terminates, that means that path is not successful, right? Even if it terminates at a final state, you are marking that particular path has not read the entire X. So it has been terminated. So for example, if you are considering the string X, and suppose for a prefix X1, you are at a final state and you have terminated, then it will not be considered that X has been accepted. It will be considered that that particular path has been terminated.
Ma'am, here we can loop at 0 till only 5 characters are remaining. And if the fifth last is 1, then we can go from 0 to 1 and so on.
Okay, that is one direction, which says that all strings from A will be accepted by the machine represented by this transition diagram. The other direction, you have to show that no other string is being accepted.
Yes, ma'am. So if the fifth last is again not 1, then we'll have to loop once more at 0 itself, and only 4 characters will remain.
Correct.
So it will not reach the final state.
Okay. So if you have to reach the final state from the start state, you need at least one. If you look at, there is exactly one path, and the property of that path is the fifth last symbol must be 1. Otherwise, you will not be able to reach the final state. Okay, so notice that when we were looking at the DFA transition diagram, then both the solutions that we had, they were similar solutions, but both the discussions that we had, we were going up to 32 states, and here we only have 6 states. So if we can capture this mathematically, this so now it seems like we can describe these things in a more succinct manner. So let's go to the...
Ma'am,
Yes.
I have a doubt in the termination of this, ma'am.
Yes, okay. Oh, okay. So you have a... Okay. So, so let's take an example. Let me go back here. Okay. So this particular DFA was as follows. Okay, so this is what the DFA looked like. Now, suppose you get the string, let's say 0, 1, 0, 0. Let's take this particular string. Can you tell me how many paths there are that are labeled by 0, 1, 0, 0? Or that are, yeah, okay. First tell me how many paths are there that are labeled by 0, 1, 0, 0?
2.
Two.
What are these two?
One will remain at the starting position only.
Okay. So okay. So what do I mean by label? The first thing is I go as 0, then I take 1, then I take 0, then I take 0. This is one path labeled completely as 0, 1, 0, 0. But remember that I'm taking paths one step at a time. So I could also have done the following. I take 0. For 1, I take this particular edge and then I'm stuck. I don't have another, or I could, okay, sorry, no. I take 1, then I take 0, and then take 0 and stay here. Okay, so I have two paths, a blue and a red path, both labeled 0, 1, 0, 0. Fine? Is it fine till now?
Yes, ma'am.
Yes, ma'am.
Okay, so now I am extending my string definition. Now I'm changing my, let me put it as 0. I'll just add a few more zeros. Okay. Okay. Now, can somebody tell me a path which is terminating? So now you realize that there can be more than one paths that are labeled by the same string. So now can somebody give me a path that is terminating? Meaning you cannot read the entire
path will terminate.
Correct. So if I follow the blue path now, I take 0, and then let's say for this 1, I take this particular arrow. Then I follow, I have 1, 2, 3, 4, 5, 6, 7 zeros. Now if I have to take a 0, I know I must go along this path, right? So I take the first 0, I take the second 0, I take the third one, fourth one. I don't have any other transitions left. So this particular string, this particular path is labeled by 0, 1, 0, 0, 0, 0, which is a substring of the input string, but I couldn't make the transition anymore. So this path has basically terminated. Can you give me a path which does not terminate, but so this is not a string that is going to be accepted, right? Because the fifth symbol is 0. So can you give me a path which is not terminating? The person who asked a question about termination, can you give me a path that is not terminating, but that does not end up in a reject state? That does not end up in the final state.
Yes, ma'am. Like when we are going to 1, we are not going to the right hand side, and we are just looping on the start.
We just loop, right. We just keep looping. Is there any path that is ending up in the final state?
No, ma'am.
No, because of the previous argument. Because in the previous argument, we saw that if we saw both directions, we saw that all strings of A will have at least one path that ends up in that ends up in the final state, and we also saw that if there is a string that is ending up in the final state, then it will. If there is a string that is ending up in the final state, then the fifth last symbol will be 1. I'll just consider one more example just to clarify.
So, ma'am, if we are given an input, then we have to check all possible paths.
I mean, you can check all paths. There can be different arguments for this. You don't need to check all possible paths. depending on the problem, so for example, here we didn't really check all possible paths, right? We gave a combinatorial argument to say that no matter what the paths are, if you want to end up in the final state, we have to use this one particular bottleneck edge, and that ensures that the fifth last symbol is 1. I am not saying that the argument will only be checking all possible paths manually, but yeah, the argument should satisfy the fact that all if it's a acceptable, if it's a string that is accepted, then there exists a path which ends up in a final state, and if it's not accepted, then all possible paths end up in non-final states, or they are
before saying that
terminated.
it is non-accepted, we have to check all.
Yes, there are two directions in which we have to argue. If you want to check if you want to argue the correctness of a particular NFA, then there are two directions you have to argue. The first is, if a string is accepted, then there exists a path that ends up in a final state, and if a string is not accepted, then no matter which path I take that is labeled by the string itself or by a substring of the string, that path will either terminate or it will end up in a non-final state. Okay, so I just want to consider one more example. So this is something which will be accepted, right? And we know one path, the blue path, will be something that reads the entire string and that ends in a final state. So this is a sort of a certificate path. The blue path is a certificate path that shows that this string is going to be accepted. Can you give me a path that is not ending up in a final state?
Yes, ma'am. Don't move forward for one and just loop at start.
The red path. Right. So there are two paths. We have at least one path that is ending in a final state. Therefore, we can say that this string is going to be accepted.
Ma'am?
Yes.
Can you please explain again the proof for from the other side, like that no other string will be accepted by this NFA? Like I didn't get that.
Okay, so if you consider any string that is starting from this, there is a unique start. So this argument is specific to this particular NFA. The argument will change for the other NFAs, for other examples of NFAs. So for this particular NFA, we have one start state and one final state. Now, if I have to reach from the start state to the final state, I must, the ending path must be, so if I have to reach from the start state to the final state, it must be through this path, this 5-length path, where if you look at the first edge, after that you can have any symbols, you can have 0 or 1, but if you look at the first edge, that must be labeled by 1. Now if you track back, it means you have ended over here. So the last symbol could be 0 or 1, second last could be 0 or 1, third last 0 or 1, fourth last could be 0 or 1, but the fifth last must be 1. So this was sort of a bottleneck edge, which ensured that the fifth last element is 1 if you end up in the final state.
Okay, ma'am. Yeah, I got it. And like I had another doubt. Like
yes,
how does the machine or the automaton understands if it's terminated because the string has got exhausted or because it hasn't read the string completely? Like these two could be two possibilities for termination, right? So like how does it identify if it's terminated without reading the complete string or if it's terminated after reading the complete string?
What do you mean by terminated after reading the complete thing?
I mean like
that so I will not call that termination. Termination is when you are termination means you are sort of switching off the machines. So the machine has stopped computing. You can think of it as you are switching you have switched off the machine and you are restarting.
Okay, so
you couldn't finish your computation, and that you can call ending. These two things are different. One is your machine had to stop midway, and the other is it finished computation and now it's ready for the next input.
Okay, ma'am. So like if a string terminates, even then also it's rejected, right?
Yes, yes. So if a string terminates, let's say, okay, I didn't understand your question. If a string terminates, then it is rejected.
Maybe I will just say something.
Yes.
So if there is such a case where you cannot move any further, but the input is still not exhausted, then we say the machine got stuck. Okay, a stuck machine cannot accept, so it is assumed to be reject. So in order to make a machine accept or reject or accept, it has to read the entire input string without ever getting stuck.
Okay.
Does it answer your question?
Yes, sir. Yes, sir.
In the intermediate position, there is no question of accepting or rejecting. There is a question of getting stuck, and getting stuck immediately means rejection.
Okay, sir.
Okay.
So just to add to that, just by looking at one path, termination is an aspect of one particular path that you're considering. But acceptance and rejection cannot be determined just because one path has terminated. It is possible that a string is accepted because of some other path, but on this path it has terminated. On this path, the machine got stuck.
Oh, okay, ma'am. Yeah, I understood the point. Thank you.
Ma'am.
So I'll give you an example. Let me give you an example. Let me see. Can I give you an example here? Yeah, I think if I change this to 1, yeah, okay. So if I change this to 1, this is still a string that gets accepted, right? Because I take this particular path. I take this loop as 1, and then I go for 1 0 0 0 0. So I end up in the accept state. So this is one path that is a certificate showing that this string is accepted. But can you think of a path that where the machine will get stuck?
A red loop.
No, not the red loop. That will terminate. That will finish, right? The machine will not get stuck over there. The red loop, it
by following the
take the straight path, not looping.
Correct. If you take
Yeah, we don't.
exactly. So if you take your first one to be this edge, then you don't know. Then you take 1, then you take 0, then 0 and 0. But for the last 0, you don't know what the machine doesn't know what to do. It's stuck. So it can only, if you take this particular edge, then it can only go up to the substring 11000. It's stuck before it can read the. When it reads the last, when it reads the last symbol 0, it is stuck. The machine is stuck. Okay, so yes.
Ma'am, the doubt was that does an NFA have a notion of set of final accepted states?
Yes, yeah. So I will come to the mathematical definition of the NFA. So far, I have just said consider DFAs. We've just made some few generalizations. The first thing is that so in a DFA you had states. In an NFA you still have states. You had input alphabet symbols. You still have a set of input symbols. Now the transition function. Now we are saying instead of a transition function, let's consider a transition map. Instead of a single start state, let's consider a set of start states. And final states, we will still have a set of final states. I just said in two places for the transition, for the set of transitions and the start states, let us generalize a little bit. So now I'll come to the mathematical.
The doubt is that let us say we have two possible final states and only one of them can be reached. Then will the string be considered to be accepted by NFA?
Yes, that's true for DFAs also, right?
Yes, yes, means that was my doubt, that what is the notion of getting accepted? Like there exists a path such that the entire string is read and you can reach a possible final state.
Yes, yes. So in DFAs, what was the condition for acceptance? That look at, there is exactly one path labeled by X starting from the start state S. So look at that path, look at the end state. If it's a final state, then you say that X is accepted. Otherwise, you say X is rejected, right?
Yes.
Now, you have a set of start states. If there exists a path starting from a start state and ending in a final state, you say that X is accepted. If no such path exists, then you say X is rejected.
Okay, ma'am, understood.
Okay, so now let me get into the mathematical definition, the explicit definition. So briefly, a priori, it seems that in this particular example, we could solve the same problem. In the DFAs, we were requiring a lot of states. In the NFA, we could solve with much fewer states. So it's a natural question whether the NFA can compute is computationally more powerful. Is it possible that there is a language which which an NFA can solve, but the DFA cannot? So before we go into these things, we need the formal definition of an NFA. So again, this is a 5-tuple where you have Q representing the set of states. The Q is the list of states. Then sigma is a list which explicitly say where you have the explicit list of alphabets, input alphabets. Now comes delta. Now the transitions I define by capital delta. So delta is a map from Q. So now delta you can think of as the following. It's a map or it's a function. No, it's not a function. So delta is a map from Q cross sigma to a set of states. Now this includes Q cross sigma. If I write 2 to the Q, if I write 2 to the Q, it is possible that Q cross sigma could be the empty state. Okay, the empty set. So you delta takes in two variables, Q, the first is a state, the second is an input symbol, and the output is a set of states. Now it is possible that there are no state. It is possible that the output set is the empty set itself. So meaning that if I take a Q and a symbol A, it is possible that no transition is defined for that particular pair. And it is also possible that Q comma A has more than one possible next states to transition to. And capital S is again as before. We don't want it to be a single state. It could be a set of states, and the final states can still be a set of final states. And again, as you see, we can explicitly define a particular NFA in finite as a finite string or in finite space. So the next thing then is to consider multi-step transitions. Just like we had a multi-step function for delta, now we want a multi-step extension of delta. So we have delta hat to be 2 to the q cross sigma star mapping to a subset of states. So notice the difference over here. In delta, your input is a single state and an alphabet symbol. In delta hat, your input is a set of states and possibly a string. So why we need a set of states is, you consider the first step. In the first step, if you look at this diagram, suppose you are at state P and you are reading input alphabet A, then you can transition to a set of states which we will be denoting as delta PA. Right? It is possible that you transition to a set of states. It's also possible that you don't have any transitions at all. In the next step now, if I want to extend it just by one more step, then I must have a definition where instead of transitioning from one state, you make the transition considering a set of states. That's the reason when I go for a multi-step extension, I need the map to be defined on 2 to the q cross sigma star.
But ma'am, at any step we can be only at one state.
So okay, what do you mean by that?
Means in delta cap also we should have q cross alphabet.
So delta hat is trying to capture a multi. So in delta, if we go back to small delta hat, the multi-step transition function for DFAs, then what was it trying to capture? It was trying to see, if I start from a start state and I read X, where do I end up? So in DFAs, it was just that I must have ended up in one particular state. But in NFAs, if you just consider one step, if I ask the question, if I start from a particular state and I read a particular symbol, where do I end up? It is the possibilities are a set of states.
Yes, ma'am. The possibilities are a set of states, but we can presently be only at one state.
Yeah, but now if you go for the next step, so now if I wanted to know, if I start from P and I want to I want to find out what happens to the string AB, then how do I go to the next step? So this delta hat, this multi-step function, if you recall, had an inductive definition, right? It was saying that if I read the string epsilon, then I stay in the same state. If I read a new alphabet, or if I read a string XA, then delta hat PXA would be delta of delta hat PX comma A. So that was the inductive step of the definition.
Okay,
I was
yes,
using the delta hat definition for a smaller string to define my delta hat for a string that is extended by one symbol. So if I want to extend it now, then I require it to be on a set of states. Because if you just look at the second step, you must extend it with from a set of states instead of one single state.
Yes, ma'am.
Okay.
Ma'am,
Yes.
how can an input be a set? Because set does not have a notion of ordering, right?
What do you mean?
Means in a set, elements are not ordered, right?
Yes, that's fine. But
then how will you decide from which state have you started and then from which state? Like there may be multiple possible outputs for
there
delta.
may be multiple possible. So you are saying that if I for delta hat, you will not know exactly which edges are there.
No, my doubt is how will we know from which state to start from for delta hat? Let us say I have a set of 4 states, but there is no such marking that this is the first state from which I started and these are the 3 possible to which I can reach.
Why not? I haven't defined. Let me show you what delta hat is, and then maybe your doubt will be cleared. So delta hat is defined in a particular way. What delta hat will answer is what are the states where you can reach. Yes, you cannot specifically say which, you cannot say from which state you have reached this particular state. So suppose delta hat answers, let's say in the third step, what are the states you can reach?
Okay, I've
So
understood the notion. I got what is happening.
So if I consider the inductive definition, then again, if I read the empty string, I stay in the same set of states. If I read a string XA, if I want to read a string XA and I want to find out what are the end states of all possible paths labeled by XA and starting from states in the set A, then delta hat gives me that end, the set of end states. So how do I define it? Delta hat A XA is equal to, you take the union over all states Q that are in delta hat AX, and then you take this particular Q and see what is delta of QA. What are the states that are reachable from what are the states in delta of QA? So what are the states that are reachable from Q in one step on reading A? So you take the union of that, that is the entire set of states that can be end states when you start from a state in A and you follow a path labeled by XA.
Understood, ma'am.
Okay, so if you just look at this diagram, this is a thematic diagram. A, delta hat AX, delta hat AXA, all of these could be intersecting each other. They need not be disjoint. I just drew a thematic diagram where you start from the set A. Your starting states are lying inside set A. You follow a path labeled by X and you reach a set of states which we are calling delta hat AX. Delta hat AX could have intersection with A. Now, in the final step, if you let's consider a particular state Q in delta hat AX, you consider all possible ways of going out of Q with an edge labeled by A. Now this new set that you construct from delta hat AX using outgoing edges labeled by A is your set delta hat AXA, could be intersecting with delta hat AX, could be intersecting with A. Okay, so the definition does not require these sets to be disjoint or anything. Okay. Any questions?
Ma'am, one more question. Let us delta hat of A epsilon is equal to A, right? So let us say I am in a particular state of belonging to the set A and I do not perform any operation. Then is it certain that I will be remaining in that same state, or is it possible that I can go to some other state belonging to set A?
What do you mean by you don't do any operation?
Like epsilon is an empty string, right? Means no.
Right.
Right. So let us say A has three states Q1, Q2, Q3. I am in Q1. I receive an empty string as input. Then can I say for certain that I will be in state Q1 after that, or like is there is a possibility that I may be in state Q2?
No, how will just from this definition, how will you reach Q2? If I just get epsilon, I don't have a way of moving forward, right?
Okay, okay.
You are only moving forward when you read an input symbol. And in this model at least, we will see another model, but in for now, the input symbols we are reading only in the beginning. We are saying if there is only if the string is epsilon, do we not move forward? If the string has input symbols, then if there is an outgoing edge from the current state, we consider all possible such outgoing edges. Otherwise, the machine is stuck. One of the two things must happen.
Okay, ma'am. Got it.
Yeah, okay, so this is just in words. And yeah, I think from the diagram itself, these two sentences just describe the diagram. So now let's look at what the multi-step extension is doing. So what is happening on length 1 strings? If we consider delta hat A and length 1 string A, just one symbol, then you can consider this symbol A to be the string epsilon concatenated with A. So that is delta hat A epsilon A. And now if you take the inductive definition of delta hat, that means you are taking union over all q in delta hat A epsilon and union of delta QA. And del Q, what are the states Q in delta hat A epsilon? It must be all the states in A and nothing else. Because if what is delta hat A epsilon? By the base case definition of delta hat, it is just A itself. So delta hat A is equal to union over all Q in A delta of QA. So in one step, delta hat is basically the union over all the delta QAs such that Q belongs to A. You're just taking look at A, look at each state in A, and your delta hat AA will be all those states that can be reachable from some state in A. All the states that can be reachable by an edge labeled by A from some state in A. And finally, what do we want from delta hat? We want that this machine N accepts X if delta hat Sx, S being the set of start states, intersects with the set of final states, which would mean that there exists a path which starts from a start state and ends in a final state. Now again, as somebody pointed out, delta hat Sx is just giving you the set of states that you have reached so far. So for example, delta hat Sx means the set of states that are end states for paths labeled by X starting from some state in S. But you do not know what is the exact path, what is the exact certificate path that accepts X. Can you tell me how you can know this? You have the entire transition diagram. Can you construct the path that accepts X? Can you hear me?
Yes.
Hello?
Repeat the
Yeah,
question?
okay. So can somebody tell me, delta hat gives me the end states for a particular string. Can you tell me, can I construct a particular path that witnesses the fact that X is being accepted?
Ma'am, we can make the start state as final state and reverse X maybe.
How do I still get the path?
Ma'am, can we arbitrarily choose one of the states from delta hat Sx intersection F and then just backtrack?
Right. So a backtracking algorithm, because you can get, so if you have X, so suppose you know for every prefix of X, suppose you know the delta, for every prefix Y of X, suppose you know delta hat Sy. Then can you construct a path?
Ma'am, could you please repeat the question?
So suppose so if you can compute delta hat, you can also compute delta hat Sy, where Y is any prefix of X. So that means at every level, for every prefix, you know the end states. So for every prefix of X, you can using delta hat, you can find out the end states of all paths that are labeled by this prefix y and starting from some start state.
Yes.
Yes.
So can you tell me a little bit more about the backtracking algorithm? How exactly are you backtracking? Like using the are you just backtracking using the transition diagram, just graphic backtracking? How are you exactly
No,
backtracking?
first we will take a state from delta sx intersection with f. Yeah, and then we will take the state delta cap s and y, and then y is a substring with just don't having the last alphabet of a.
Correct, yeah, like that. Yes.
Yes,
So
ma'am.
this is how you can do it. Okay. So in fact, you can construct this particular, if such a path exists using delta hat on the different prefixes of x, you can reconstruct this path. Okay, and then finally n is the language accepted by n is the set of strings that n is accepting. So let us understand this delta hat a little bit more. Remember, for the multi-step function for deterministic finite automata, we wanted to see what happens if I have a string that has, suppose I have a string z which is actually x concatenated with y. We wanted to understand, so intuitively it should have been that delta hat, let's say delta hat qx, delta hat qxy is equal to delta hat of qx comma y. So it should have been that the path labeled by xy should be the path labeled by x concat and followed by the path labeled by y in the transition diagram. So here does similar things happen because there are many paths now. So is it still true? Is something similar still true? So the statement is for any x comma y, any strings in sigma star, any two strings in sigma star, and any subset a. So this is like a starting subset uh, of q. I won't say starting stuff. A is not a A is not the set of start states. A is just any subset of q. For any subset of q and any two strings x and y, delta hat a x y is equal to delta hat of delta hat ax comma y. Let me see if I have, okay. So here, what does this mean? Look at the end states of the string, end states of paths labeled by xy starting from some state of a. Then this should be same as look at the end states of paths labeled by x starting from a. Consider, let this set be b. This delta hat ax, let this be b. Now look at the end states of paths labeled by y starting from b. This should exactly be, this set of end states, let's call this C, should exactly be delta hat AXY. Intuitively also this seems correct, right? Any path that is labeled by XY can be deconstructed into a path labeled by X followed by a path labeled by Y. And this, the end state of the path labeled, the subpath labeled by X should belong to delta hat AX. So intuitively this seems correct. And formally, if you want to prove it, you have to prove by inducting on the length of y. I won't go into the steps of the proof. Please go through it yourself. Try to prove it yourself, and then if not, then go through it yourself. Another simple observation is that suppose I want to look at what happens to delta hat ax in terms of each state in A. So delta hat AX describes the set of states, the set of end states for paths labeled by X starting from A. But this, if you consider these paths, you can divide it into the so you can divide it into paths that are, so suppose A has states q1, q2, q3, q4. The paths that are going out of A labeled by X can be also thought of as paths that are going out of q1, union paths that are going out of q2, union paths that are going out of q3, union those going out of q4. So intuitively it should be that delta hat Ax is equal to union over all the states that are in A, delta hat Px. And in fact, you can prove this as well by inducting on the length of X. Again, I will not give you this proof. So now using this notion of NFAs, and we also saw a little bit of what the delta hat what delta hat is doing. Now let us try to tackle the problem of whether NFAs can solve any problems which whether there is an extra problem that an NFA can solve but a DFA cannot. Notice that a DFA can be thought of as an NFA. If you just describe the DFA to be Q sigma delta a set of start states containing only the single state S F, where delta is doing the following: capital delta PA is equal to the the end states in capital delta PA is just that single state, the only possible transition state of delta PA. So a DFA can be thought of as an NFA. DFA is definitely a special case of NFA. So if a set is accepted by a DFA, you can say that it is accepted by an NFA. But what about the other direction? If a language is accepted by an NFA, then is it accepted? Then can I design a DFA accepting it? So what are your thoughts?
Ma'am, can we assume an FA as a set of DFAs?
NFA as a set of DFAs. What do you mean? I did not understand.
Like set of DFAs with different starting states.
But even within that, you can have, you're still not solving the, yeah, sure. You can say that, okay, this is one way of thinking of it. I have multiple start states. Let me just consider what is the reachability from each of the start states. But the entire thing can be connected, right? How will you extract the things? And the second point is, from a particular state, you can have multiple outgoing edges labeled by the same alphabet. How do you resolve that issue?
Ma'am, what we can do is that let us say we have a set of start states and a set of final states. So like for each pair of start state and final state, and like for all possible paths, we can construct a DFA. Right.
How many DFAs will that be?
Means anyways it will be a finite number, right? Because everything, right? So union of finite DFAs is also a DFA, so we can say that.
No, once more. So you are considering, you
us say
consider one start state.
Means for all possible pairs of start state and end state. Like now, the problem is that there may be multiple paths for a single alphabet from a particular state, right? So what we do is that for each possible path, we construct a new DFA for that particular start and final state and take union of all these.
So suppose from a start state to a final state, in between there is a loop. So are you going to consider that loop as well? So are you saying that a particular DFA will accept one string, or it accepts a set of strings? I did not understand your constraint.
Means let us say we have from a, like in NFA we have a concept that if we have a state and if we have an alphabet, then there can be a set of possible outputs, right?
Correct, yes.
So for each possible output, we create a new DFA, and for each possible set of start and end final state, right? So we just extract out different DFAs from the NFA.
Okay.
And then we take the union of all those because a output will be accepted by one or more of those DFAs, right? So finally we can get a DFA out of that NFA.
Okay, okay, okay.
Ma'am, but will it be finite? Because suppose in the
How
example,
are you? Yeah,
because,
okay, what is your question?
ma'am, because in the first example that you gave, like the first state, and then we loop if it is 0, 1, means we stay in the first state. So because we can input as give the first symbol as 0 and stay in the first state, then again give 0, then stay in the first state. So this way we are going to get infinite DFs, right? Because we are not going to.
No, I think what he's saying is you will include it as a loop. So I think what he's saying is over there it will be. Yeah, okay. What? So suppose there is a loop, then where are you including this loop?
Like what my thought was that for I will have to think about this loop thing once again.
And the second question is, okay, so suppose you can get multiple DFAs, that still does not answer my question, because my question was, can I get one DFA that solves this problem? You have
Then we
a
can
set of,
just take union of all of the
you will
DFAs.
do the product construction.
Yes.
No, sorry. Oh, union of all.
Union of all of
Okay.
them.
Okay. So if you could get finite DFAs, then you will try to do the union of each of them. So can you get finite DFAs? How can you get finite DFAs? This looping, if there is a loop, there seems to be a problem in extracting just in terms of paths.
Ma'am, like what is the thought is like for let us say you have a state, two states Q1 and Q2, and like if you get a 1, you will have two possible paths. From Q1 you can go to Q2 or you stay in Q1, right?
Yes.
So there are only two possible things that can be happening. So how will this reach infinite, right? In one of the DFI keep a loop, and in one of the DFI go to
Okay, so
Q2.
you just try that particular, you just try
Ma'am, like, but
the
then
example
that,
we considered, that loop followed by a path. How many DFAs will you get?
ma'am, in that case, like what he's saying, that we'll separate the loop DFA and the one with straight, like which has direct path. Then what about the input in which,
Then we
like,
won't.
yes, ma'am, like,
Then we are not accepting all streams.
yes, ma'am, like there might be input where like we are looping once and then we are going on the path, on the different path, right? Like in NFA, we do all possible paths. So that kind of strings won't be included in if we separate all the
Right.
DFAs.
So you have to, you're right, you have to capture these paths. There are multiple paths. You have to sort of capture these paths in some way to make it into, you have to collapse all these paths into one super path. And another information, as somebody said, if I can get a finite set of DFAs, then I will be able to do union and show that there exists a DFA. I can construct also. So what can we do?
Ma'am, can we create the power set of Qn as the states of a DFA and define the transition function as delta hat a, comma a single alphabet?
So why are you thinking of power set?
Ma'am, I think it kind of like incorporates the idea of multiple paths into a single path somehow.
So it is sort of incorporating what delta hat is representing, right? Delta hat is representing a subset of states where you land up. Delta or delta hat, both these things represent a set of states where you land up. So
Ma'am, I think you are not audible.
Ma'am, you are not audible.
Can you hear me now?
Yes,
Yes.
1 minute. Can you still hear me? Hello?
Yes.
Okay, okay. Okay, what was delta hat doing? It was actually capturing this set of paths in the following way. You look at x is equal to x1, x2, and so on. So what delta hat was doing is, if you consider delta hat s x1, it was considering all the subpaths of length 1. So look at all the paths that are labeled by x. Look at this all possible subpaths of length 1 of those paths. So that was the first set, delta hat s x1. So you can deconstruct these paths as delta hat s x1, delta hat s x1, x2, and so on, right? So now if I capture these delta hat, the sets delta hat sx1s, then I should be able to follow, then it seems like I should be able to follow, I should be able to create a unique path for a DFA starting from a start state. Start state will also be this corresponding to this subset of start states of the NFA, and ending in a final state. Now the final state here, we require at least one final state. So the final states in my DFA, the possible final states could be all those subsets which contain at least one final state. Then then maybe a DFA can be constructed. So now let's get back to the formal definition. So this is the DFA construction. You take your set of states is the power set of Qn. Okay, so I started with n, which is an NFA, Qn sigma delta n Sn Fn, and the language being accepted is Ln. And now I'm going to construct the DFA. Can you still hear me?
Yes, ma'am.
Yes, ma'am.
Okay. So now I'm going to construct the DFA. M, the set of states is 2 to the Qn. Then you have the same alphabet. And now I'm going to define delta M Sm Fm. Sm Fm I sort of already mentioned. Sn is the state corresponding to the subset Sn. Sn was the set of states of the NFA. Fm will be the states corresponding to subsets that have non-empty intersection with Fn. And delta will be delta M AA. So if I'm at the state corresponding to the subset A and I'm reading the alphabet A, I should be going to the state corresponding to the subset delta hat N AA. So pictorially, that's what we were aiming for. Any questions so far?
And could you explain SM once again, the state corresponding to the subset SN? I didn't get this thing.
SM is just, so you have the subset Sn is the set of start states for N being the NFA. So for the DFA, in the DFA, what are the states? Each state corresponds to a subset of states of Qn. Now consider that state that corresponds to the subset Sn. That is my start state in my DFA.
Okay, ma'am.
Similarly, FM is a set of states. What do these states correspond to? Each of these states correspond to a subset of Qn. So when will I include a state of this DFA M into Fm? When this corresponds to a subset of Qn that has intersection with Fn. Fn was the set of final states in the NFAN. Okay. And is the transition function clear? We are trying to capture one step of the transition map delta delta hat n, and what that means is I start from a set of I start from a subset of Qn and I reach a subset of Qn, and that subset will be delta hat n AA. If I started from the subset A and read A, symbol A, then I would have reached delta hat n AA. Now, in my DFA, my transition should be, you consider the state corresponding to A. If I'm at that particular state and I'm reading A, then I should be going to the state that corresponds to the subset delta hat n an AA. Fine?
Ma'am, but delta hat and AA may be a set, and delta MAA should be one state only.
Right, but if you look at the set of states in M, each state corresponds to a subset of Qn. Delta hat NAA is a subset of Qn. So I have a state corresponding to that particular subset.
Ma'am, is it necessary that all the subsets of Qn will be a state in DFA?
Necessary as in I am just constructing
Means
it in
we may
this
not
way.
get
Some
at
of
that
them
subset anytime.
anytime, yes. There may be a state in this current definition. There may be a state in the DFA which does not have any incoming edges, does not have any outgoing edges. That's possible. I'm just giving you a particular construct.
So is that possible in DFA? That a state don't have incoming and outgoing edges?
So let's see what happens.
Okay. Ma'am, you are not audible.
Ma'am, you are not audible.
Can you hear me?
Yes, ma'am.
So can we go back to the last question? What was your question? You said that for it is possible that for some subset of Qn, it's not reachable, or you don't have for
Yes,
some
ma'am.
subset of. But if you consider a subset of Qn, so if you look at delta hat, if you look at delta, what was delta doing? Delta was taking in a state Q and an alphabet A, and it was defining a subset. That subset could be empty.
Yes, ma'am.
So here in 2 to the Qn, you have a state that corresponds to empty state, right? For that corresponds to the empty set.
Yes, ma'am.
So have I answered your question? There, if you don't have any such transition, you will go to that empty state, to the state corresponding to the empty set for that particular alphabet.
No, ma'am, I'm asking like in a DFA, is it possible or is it allowed that we can define some states which don't have incoming and outgoing edges?
No, that's not possible.
No.
I mean, incoming is not outgoing must be there. For any in a DFA, if you have a state, you must have outgoing edges. Incoming there may not be any incoming edges, but you must have outgoing edges.
Yeah. So
then ma'am, here also like I'm thinking there.
Yeah. Let me just interrupt. So there may be unreachable states. Unreachable means unreachable by any labeled string from start state. It's possible. In fact, we will see that this DFA construction, this so-called NFA to DFA construction, that is called the subset construction or something like that. This often leads to many unreachable states. So you simply throw them out.
Okay, sir. Thank you.
Okay,
but
so
that
was
yes.
your question, right? It's possible to have unreachable states.
No, I think his question was what happens if we don't have any outgoing edges, because
No,
that is what is.
No, that's not the question. Outgoing edges must be there.
Yes.
By definition, in a DFA, all outgoing edges must be uniquely present. But unreachable.
Yes, sir. So while we define a DFA for an NFA, it is guaranteed that all the sets will have an outgoing edges.
Yeah. So can you tell me why that? Can you tell me why that will happen? Where do you think outgoing edges will may create a problem?
Ma'am, that depends on the delta cap function actually.
No, but so if you're just looking at one step, if you're just looking at delta hat NAA, where can an outgoing edge create a problem? Where do you think in the DFA there will not be an edge? Only when delta hat NAA is an empty set, right?
Yes, ma'am.
So then you have a state in 2 to the Qn that corresponds to the empty set. So you go to that state.
Then what about the other?
What is the other? What do you mean other?
I mean the other sets. Where will they point to?
No. Okay. Okay. Let me consider two parts. First part is there may not be any incoming edges. There may be some states where there are no incoming edges. This is possible.
Yes.
But in a DFA, you need outgoing edges for every alphabet. For every symbol in your alphabet, you need exactly one outgoing edge from that state.
Yes, ma'am.
So can you tell me a scenario where there will not be such an outgoing edge for a particular alphabet?
Ma'am, I will think for an example.
Yes. Okay. So I'll just tell you that in 2 to the Qn, this empty set is also represented as a state.
Yes, ma'am.
Now you think about.
Ma'am?
Okay. Yes.
Ma'am, in NFAs, we might have a termination, right? Like from a state, there are no other, like no transitions.
That's true, but that was not being captured by delta hat anyway. Delta hat was all those states where delta hat S, X, but all those states that you can reach when you read X. The termination points were being left out much earlier, maybe for some that those states may appear in, let's say, delta hat SX1 where it got terminated, but it would not have been represented in delta hat SX.
Ma'am, but for the DFA, like for a given state, suppose we are given a input alphabet from a state. In an NFA, suppose it terminates for that given input alphabet. So like what will be that equivalent in DFA? Like we would have to somehow end the process of moving, right, in DFA.
So you're saying if a string cannot be read at all,
Ma'am, like
all the
suppose
paths terminate.
like suppose in NFA we can have a state where when we get an input alphabet, it terminates. Like there are no other transitions for that input alphabet from that state.
So is your just one path is just one path is not your question, right? Your question is what happens if every path for that. So if you consider X, the string X, what happens if there is no path labeled by X? This is your question?
Yeah, ma'am. Like in NFA, like there can be paths where like, I mean, like if there is an input alphabet, there can be a case where there is no transition defined for it, right? In NFA.
Sure. Yeah. So what does that mean? If suppose there is a path that is terminating. Okay, so suppose there is a path that is terminating. You consider X, you consider a string X. Suppose there is a path that is terminating, and suppose there is another path that is labeled by X. So what will delta hat Sx contain? Suppose that there is a path terminating at, let's say, Q, and a path that is ending at P. So what will delta hat Sx contain? Just from the definition, what will delta hat Sx contain?
It will contain only the labeled path.
Only?
The labeled path. Like,
meaning it will only contain P, not the labeled paths. It will contain P.
Yes, ma'am.
Okay, so now if you only had a path Q and it was terminating, the machine would get stuck at X. What is delta hat Sx?
It will be Q, right?
No. What will delta hat Sx be? Q is a path labeled by a substring of X, by a prefix of X. What is delta hat Sx?
Delta hat Sx is basically the state at which you end up after.
No. The delta hat Sx is the state at which you end up after reading X. You consider the definition of delta hat Sx. Let's go back.
Delta hat Sx would be null.
Correct. Delta hat Sx will be the empty set. If you consider the definition of delta hat
when it is an
Sx,
empty set, so we say that there is no arrows, we can say. No transition.
Yeah, there are no paths. There are no paths labeled by X. If you look at the inductive definition of delta hat, what is the inductive step? Inductive step is saying you move back one step. Look at those. So you suppose you have reached a certain set of states of delta hat Ax, then you take one more. You take all outgoing edges labeled by A. Whatever you reach there, whatever is the set of states you reach, that is your delta hat Axa. So if your machine gets stuck at all the paths at X, then you don't reach anything out. Then the set of states which is reachable with an outgoing edge of A is empty.
So basically, if there are no outgoing sets, it will end up going to the empty string.
Going to the empty string.
Empty set.
Meaning delta hat Ax will be an empty set. Now in the DFA, that means I'll end up in the state corresponding to the empty set.
Okay, ma'am, got it.
Yeah, okay.
And what will happen after that? Can you answer? Once you end up in that empty state, what will happen?
It should loop in that empty state because it got terminated.
Right. By definition, it should loop. And it can never be a final state. Right?
Yes, sir.
Right. Final state must contain a final state of the NFA. Yeah.
Okay. So we were here. Okay, so now we need to prove, if we have to look at what is the language defined by M, the DFA we are constructing M, we need to understand the multi-step transition function. And for this, we have to prove this following lemma. If you take any subset A of the set of states in, if you take any subset of QM, the set of states in the DFA-M, and you take a string X, then delta hat M AX is equal to the state corresponding to delta hat N AX, capital delta hat N AX. So basically, this will prove that you are exactly reaching, if you are reading this the set, the string X, and you're starting from a state corresponding to a subset A. Okay. Yeah. Okay. So sorry, there is an error here. You consider a subset A of Qn, meaning it's a state in Qm. It's not a subset of Qm. You consider a subset A which belongs to 2 to the Qn, which means it's a state of Qm. Then delta hat M AX is equal to the state that corresponds to the subset delta hat N AX. Meaning that if you started from the state corresponding to this subset A and you read X, then you should end up in the state corresponding to the subset delta hat N AX, which is all the possible end states of paths labeled by X starting from the subset A. And intuitively, this should be fine for you by now. And if you have to prove it, you induct on the length of X. So this is more or less in most of the proofs in this section, you will have to do some induction, some kind of induction proof, usually on the length of the input string. I will not go through this again. And now that we understand the multi-step function delta hat M, now it will be possible for us to prove that the same set of strings, the same set is being accepted by M and N. And how do we prove this? So if X is an LM, this will be a double arrow. This will be an implication symbol. X is an LM if and only if delta M SM X belongs to FM. Meaning, if X is an LM, the definition of X being an LM is that delta hat M SM X is a final state in the DFA M. Now, this happens if and only if delta hat SMX, this the subset of Qn, the subset corresponding to delta hat M SMX. Delta hat M SMX is a state in the DFA M. That means it is a subset of states in the NFA N. Consider that subset that has a non-empty intersection with Fn by definition. Then that means delta hat N SNX intersection Fn is non-empty. Okay. And delta hat N SNX intersection Fn is non-empty means that S belongs to L of N. So we started with a language which is in L of M, and we show that
Ma'am, you're not audible.
Can you hear me now?
Yes, ma'am.
Okay, so we proved that, how much did you hear? We proved that the same set of strings is accepted by M and N. The basic idea is you take a string x of x which is in LM. This means, by definition, it means that delta hat M SMX must be in the set of final states in the DFA M. Now, the set of final states was defined in such a way that it means that you look at the corresponding subset in Qn that has at least one final state of Qn, meaning the NFA N. And that would mean that X is being accepted by Ln. So therefore, the same set of strings are being accepted by M and N. Okay, so then we can conclude for every NFA, we show that we are able to construct a DFA. So then that means that NFAs are also accepting regular states. They do not have more computational power. You give me any regular set, we know that is there exists a DFA that accepts it. So we saw that a DFA is a special case of an NFA. So a regular set is accepted by an NFA. You give me a set that is accepted by an NFA, we know that it is also accepted by a DFA, this particular DFA that we constructed, and therefore it is a regular set. So NFAs are also accepting exactly regular sets. NFAs have exactly the same computational power as DFAs. Now we are going to be looking at a slightly more generalized version of NFAs, which is called NFAs with epsilon transitions. So here we will also allow spontaneous transitions, meaning that I don't read anything from the input. I just make a transition. So such edges I will label with epsilon, as if I have just read epsilon and I'm making that transition. I'm not reading any of the input symbols. So just as an example, this does not really show, this just shows that epsilon transitions make it easier for us to visualize an NFA. If you look at the problem X contained in A star, such that the length of X is divisible by 2 or 7, then then one way of doing it is I construct a DFA for the set of for the set of strings that are whose length is divisible by 2, and a DFA for the set of strings whose length is divisible by 7. Now I do a construction for the union of these two languages. A simple way of doing it is you use epsilon transitions. So you have this, you have the loop on the left hand side with two states that represents strings that could represent strings that are accepted for the length being divisible by 2, and the 7-state cycle on the right hand side that could accept strings of length strings whose length are divisible by 7, and instead of doing the product construction or something similar to the product construction, you can simply take a separate start state and make an epsilon transition to relevant states in the two cycles. So this makes epsilon transitions are for now. So you know that this problem can be solved by an NFA, can be solved by a DFA, but the epsilon transition makes the diagram much cleaner and it makes it more intuitive. That I decide, I'm sort of guessing whether it is going to be divisible by 2 or it is going to be divisible by 7. For all those strings that are accepted, I'm guessing whether it's going to be divisible by 2 or divisible by 7, and then I'm making an epsilon transition to the correct cycle and accepting that string. So epsilon transitions make, at least for this problem, it is making the diagram much easier, more intuitive. But do they actually increase the power of an NFA? So actually, they do not. you can, if you have an NFA with an epsilon transition, you can construct an NFA by getting rid of these epsilon transitions. You can prove it inductively, but just by looking at the transition diagram, what should you do if you want to get rid of epsilon edges labeled by epsilon?
We can copy all the transitions from the next state to the current state.
No, so for example, if you have state Q1 going with an epsilon transition to Q2, and then Q2 takes an edge A to Q3, then what are you suggesting?
If we encounter the alphabet A, then we can go directly from Q1 to Q3.
Okay, so one suggestion is, so for in an NFA, suppose you had Q1, Q2, Q3, and you had an epsilon transition here and labeled by some A, then one suggestion is you put an A over here. Okay, what do you have to do if you have to, suppose the language had epsilon in it, and maybe it was being accepted in the epsilon NFA with epsilon transitions, maybe it was being accepted because of the following. This is a start state. There could be many start states, and none of them are final states, but there is some epsilon path that ends up in a final state. So how would you accept epsilon? How would you construct an NFA for a language that contains a epsilon, but now this NFA cannot have any epsilon transitions? Notice that in the epsilon transition, NFA with epsilon transitions, epsilon is getting accepted in something other than a start state. So how will you do this?
So can't we make the start states themselves as end states?
No, that's not possible. Then you may be accepting many other strings. There could be some loop over here for which you're accepting many more strings. So what can you do? It's just one string epsilon that seems to be creating a problem.
Ma'am, can we make the epsilon states as the start states?
Epsilon states as the start states.
Yes, ma'am. The like epsilon transitions, like where we are going after an epsilon transition, we can make them as the start states.
What about the original start states?
Ma'am, if there are only epsilon transitions from the original start states, we can.
No, there need not be only epsilon transitions from the start states. There could be many other kinds of transitions from these states as well.
Yeah, then we can keep them in, like in NFA, we can have multiple start states.
But we can accept more than the required language, right? Because we are including something more. We are including a state. We are increasing the subset of start states. So we could accept more. We don't know what the NFA looks like.
Ma'am, can we copy all the start states and then make a copy of all the start states and then copy all the transitions and see whether if epsilon is supposed to be accepted, then make those a part of the end states as well, and if they are not, if then
no,
if
but you
epsilon...
can't make them. Oh, okay. Copy all the so you have so suppose you have this one NFA with epsilon transition. You have some start states. You're saying copy these start states.
Yes, ma'am. We will copy the start states, and we will the previous start states will no longer be start states, and the transitions from of the copied start states will be the same as the previous start states, and if epsilon is supposed to be accepted, then we make the copied start states as a set of as final states as well, and if epsilon is not supposed to be accepted, then they are not.
No, I am not getting your construction.
Ma'am, so basically we
how are you proving that the same language is being accepted?
Anything greater than any input greater than 1 will just have the same path except the first edge of the path.
So then why did you do these copies? Why did you make these copies? Okay, just tell me a basic question. So suppose you have an NFA. Suppose you have an NFA and you want to accept, so suppose this language is L of n. And you want to accept L of n union a particular string X. Can you design an NFA that accepts L of n union X?
Then we can convert the NFA to a DFA and then use the union operation.
You are not audible.
And you are not audible.
Can you hear me now?
Yes, ma'am.
Yes, ma'am.
So my question is, can you have multiple states, start states in an NFA, right? So in this particular NFA, you have multiple start states. You just want to accept one more string X. What can you do? Can you build an NFA very easily? Can you extend this NFA? What will be an NFA for accepting X?
A linear path that contains
Exactly. Right. Linear path that contains X. That's all. So now what will be the NFA for ln union X?
these two disjoint NFAs making the start states as
correct. This is my start state, and my final states will be final states of this plus this final state. Okay, so now answer my question. If I have a language ln and I want to ensure that epsilon is also accepted, what will I do?
Create a singleton vertex.
Exactly. So you try to prove this formally as well, that epsilon transitions do not add power, but this is the basic idea that if I mean if I can reach a state because of an epsilon path and then a labeled edge, a symbol labeled edge, then I will put a direct edge to that particular to that particular state. But it is possible that epsilon may not be still be accepted in the constructed NFA. For that, you just add a new start state, and that will you just add a new start state that does not get linked to anything else. It's just a singleton start state that will accept epsilon. So please prove this for yourself. And I'll just end with two last comments. Now that we have epsilon transitions and we know that NFAs with epsilon transitions have the same computational power as DFAs, meaning NFAs with epsilon transitions are also accepting exactly regular sets. So now if I want to check whether given two regular sets A and B, can I construct a DFA? Can I check whether AB is a regular set or not? Now I can define an NFA, easily define an NFA with epsilon transitions for the language AB and show, and this will prove that it's a regular set in the following way. I have LM1 which accepts, I have M1 which accepts A, M2 which accepts B, and now I just put a copy of M1, the starts and make epsilon transitions from the states of M1. From the final states of M1 to the start state of a copy of M2. And in this new finite automata for AB, the start state of M1 is going to remain the start state of the new automata, and the end states of M2 are going to be the end states of this new automata. Then this will accept AB and show that AB is a regular set. Similarly, if we wanted to see that A star is a regular set, we can make a similar construction. So I just want to point out that this epsilon is not correct. This epsilon edge is not needed. This particular epsilon edge is not needed. You just create a new start state, make an epsilon transition to the old start state or states, and from the old final states you put an epsilon edge to the new start state and make that the final state as well. That is the new start state, that is the new final state. So then you will be able to accept A star. And if you can accept A star, I think you will be able to construct how to accept A plus, which is A concatenated with A star. Any questions? Okay, so in this class we had there were two questions that you may want to think on your own. The first thing is, if you look at the DFA for the language containing all strings X of 0, 1 star, where the fifth last symbol was 1, then we constructed a DFA with 32 states. Can you can you construct a DFA with less number of states? And how less can that be? And the second thing is, if I consider NFAs with epsilon transition, prove formally that they are also accepting regular states. If there is a regular set, then obviously I can define a DFA as an NFA, as a special case of NFA with epsilon transitions. But if I am taking a language that is accepted by an NFA with epsilon transitions, I can also construct a DFA for that particular language. Please prove that for yourself. Okay, so that's the end of today's lecture. We will have a tutorial on Thursday at 8 AM. Thank you. I'll end the meeting.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.